Finally made it. We're ready to start talking about reactions. We're going to start with precipitation reactions. So precipitation is the formation of a solid. We've actually seen these kinds of reactions before in lab, where if you take two liquids, mix them together and you form a solid. We've said that when that happens, if you mix two solutions and you form a solid, that's a sign of a reaction. And that type of reaction is called precipitation. You start with two homogeneous solutions, two homogeneous mixtures, two solutions. For example, in this case, we have barium nitrate and potassium chromate. Chromate's just a polyatomic ion. And so we know that the ions in the reactants, because it's aqueous ionic, that they are floating around in solution right there, just kind of free doing their own thing. You know, the numbers are there, but they're free to interact in their own way. When they mix, if you pour them in, now all of the ions are in the same beaker. So they're all in the same beaker. They have the potential to interact with each other. And what that means is they can trade partners. And there are new potential combinations of ionic compounds. And particularly, you can make a new potential combination that isn't soluble anymore. You started with two soluble compounds in unique containers. You have ended up with one container where all your ions are contained, and you have created an insoluble compound, so it doesn't stay dissolved, it forms a solid. They collect together and form a solid that would now be, just kind of at the bottom of your container. I do want to make a note when we get into this, as we're going to talk about this, we're going to deal with a lot of ionic compounds. And you can see we have this ionic formula, and where we've represented a full ionic compound and then put a Q after it. What that means is that it is an ionic compound that is dissolved. We know that in the reality, if you could zoom in, those ions are floating around separately from each other. But we use this overall molecular description just to be clear as to what's going on and to make it kind of short, right? To make it compact. It's barium nitrate. You have to recognize it is implied that those ions are floating around independent of each other. So we always want to have that in the back of our mind. Whenever we see that, those ions are free floating. Solid, that's not. That's a solid, not dissolved. But AQ after an ionic compound does mean those ions are floating around freely in solution, independent of each other. If we look at another example, we could see, for example, potassium iodide and lead to nitrate. Again, we literally have 2 beakers. They are separate solutions. When we pour them in, what can happen is you trade places with which ions are paired with what. That allows for the mixing that can lead to an insoluble compound. Lead to iodide in this case, that's a very nice brightly colored yellow. Here we can see, and so that yellow solid starts to form immediately. You get that because those ions don't want to stay dissolved in solution. They're happy to form a solid and leave the solution. You get a nice crystal structure that it looks like. One of the things you'll note, it kind of looks almost gooey, or kind of like this, like it doesn't form like a brick solid. That's because it reacts so fast. It makes a bunch of really small bits of solid, and they just kind of float around. That's why it looks cloudy, and over time, they separate out to the bottom of the solution. They sink, gravity, they just sink to the bottom. One thing to note, a precipitation reaction is all about forming a solid. If you want to communicate that, you're going to need to include phases. This is combustion reactions. We could get away with dropping our solids. You can't here. You need to show that solid to show what happened. What was the precipitate? What was the precipitate? What is the solid that formed? It's lead to iodide in this case. So the important thing about these precipitation reactions is they follow that double displacement reaction pattern that we talked about. You have the ions, and all that happens is you trade partners. So barium was paired with nitrate, then potassium was paired with the chromate. They just trade. So the barium and the chromate are coming together. When you mix ionic solutions, really that's the main thing that can happen is swap. We know that barium can't be paired with potassium. That wouldn't work because those are both cations. So barium's already paired with this nitrate. The only possibility is it swaps and pairs with the other anion, which is chromate in this case. At the same time, the other pair, potassium and the nitrate, start to pair up, right? That's the only real possibility of a new compound. So you can do this double displacement pattern. Same thing happens at the potassium iodide and lead 2 nitrate. the potassium and the nitrate can pair up, and then the lead-2 and the iodide can also pair up. It is all about swapping partners. That is the double displacement pattern. Importantly, ions aren't changing identity, only swapping. Let's look at an example. Write an equation with phases for the reaction between barium chlorate, which is BaClO3, 2, and lithium phosphate, Li3PO4. Both are aqueous. All right, so we want a chemical equation. We've seen this before. We know that means we want reactants and we want products. Well, what are my reactants? Well, it's going to be the BaClO3, 2 and the lithium phosphate. I'm explicitly told that I'm doing a reaction of those things. So what are the products? So what I want to do here is I want to recognize that these are ionic compounds. Barium and lithium are both metals. They're paired with polyatomic ions here. And so this is going to be a double displacement reaction. When I have a double displacement, that means I swap my ions. So I need to recognize what are the ions that are contained in here, and then how can they swap. I do the cation with the other anion, and I swap between the two. And then I form products from those pairs, which I can do using the crossover method that we talked about previously for determining the formulas of ionic compounds. After that, I want to balance, and I need to add my phases. When I'm dealing with phases, I know that in general, I'm given them for my reactants here. They're both aqueous. For the products, determining the phases is based around solubility. Soluble things stay aqueous, they stay aqueous. Insoluble things turn into solids. So that's the setup. Let's actually work it out, see how it goes. All right, so we want this equation when we're reacting barium chlorate and lithium phosphate. So we know if we want an equation, follow our format, we want reactants and products. So we're given our reactants. We don't need to overcomplicate it. Barium chlorate plus lithium phosphate. Okay, so we've already talked about this, but when we see this, if we were just shown this and we want the products, what we want to key in on is that this is ionic. This is ionic. Because they are both ionic compounds, the reactivity pattern is going to be double displacement. Or what you're going to do is you have cation-anion pair, cation-anion pair, and you're just going to swap them. Okay, whatever. And so the barium is a cation. It has to go with the other anion. You don't do cation-cation, you do cation-anion. So the barium goes with the phosphate, and the lithium is going to go with the chlorate. Okay, so this is why we want to be able, we'd spent all that time previously talking about identifying ions in your substance. So we know we have Ba2 plus is going to go with PO4 3 minus, and Li plus is going to go with ClO3 minus. And so we can do, you know, our crossover method that we've used previously to go from the ions to figuring out the formulas. And this, whoops, let's switch back. Ba gets the 3, that's on the phosphate charge. The phosphate is a polyatomic, so that charge becomes the subscript. The 1 and the 1, ClO3. And so by identifying what the ions are in our reactants, knowing that we follow a double displacement, we can go ahead and say that our products are going to be Ba3, PO4 2, plus LiClO3. I left a lot of space there. Maybe you can figure out why. Guess why. We'll see how it fills up. So barium phosphate and lithium chlorate are what we're going to mix. So this, if we got here, I saw a couple of this is good. If you can get, even if you don't get the subscripts right, if you just know barium goes with phosphate and lithium goes with chlorate, if you didn't include the 3 and the 2, you're still on the right track because you're getting the double displacement pattern. So recognizing we need to do double displacement, making them. Then adding the subscripts, getting the right ionic compounds, good next step. So this right here, though, is not quite complete. There's a couple things we're missing. One, we were told we needed phases. So in order to figure out phases in this world of ionic of reactions, we're dealing with ionic compounds, we return to our solubility rules. There are 2 possible phases, aqueous or solid. Basically the deciding factor is, are these things soluble or not? So barium and phosphate, is that going to be a soluble compound? Lithium and chloride, is that going to be soluble? We know that these are aqueous because we were told they were aqueous. You could figure it out. Sometimes you would need to figure it out. Generally, for these sorts of precipitation reactions, ionic plus ionic, everything's going to start aqueous, and then you're going to end potentially with something that's not aqueous. So barium phosphate, we have Ba2+, PO4 3-. Barium doesn't have any special rules associated with it. Phosphate is where the rule kicks in, rule 6. Compounds with a 2- or 3- anion. So if we look for our phases, we have that 3- right there. And so that makes barium phosphate is insoluble. And so because it's insoluble, the phase is solid. This is aqueous chemistry. It's happening in water. Barium phosphate isn't going to dissolve, so it stays solid. It does not dissolve. Lithium chlorate then, lithium, that's group 1A. So when we see the lithium right here, that is going to be soluble. So lithium chlorate gets AQ. So we were explicitly asked for phases, aqueous, aqueous, solid, aqueous. One thing to note, when we're looking at reacting 2 ionic compounds, this reaction is called a precipitation reaction. Precipitate is the solid that forms. So you should always expect that at least one of your products will be a solid. There's kind of we have a tendency just to start throwing AQs everywhere because, hey, we're dealing with aqueous chemistry. But if you are looking at a reaction, ionic plus ionic, you should always expect at least one of your products will be solid. You can actually come up with reactions where everything is solid. You leave nothing dissolved. That requires a little more it's less common. Normally we'd expect to get one solid product and one aqueous product. So if we get aqueous, that's a sign that we haven't done something right. Formed a solid, and we've talked about in lab that forming solid is a sign of a chemical reaction. So if you don't have that this isn't a chemical reaction. So we'd always expect that. So if we got this far, we're in good shape. There is one other part that is not in the prompt, but we talked about previously, and that is balancing. You have to balance this reaction. So barium, I got 1 over here. There's no subscript. I got 3 right here. So I need a 3 on that. I'm going to jump to lithium. I have 3 lithiums right here. So I need 3 on that. Wait, no, let's do the chlorine. Okay, so chlorine is a complicated one here. 2 applies to this chlorine. So there are 2 chlorines per form. And I got a 3 out front. So 3 times 2, I have 6 total chlorines. Okay, so 6 total chlorines. Means when I come over here, I only have 1 in this. So I need a 6 right there. We didn't need to skip chlorine. I got confused. We will skip oxygen. So that's where we come to lithium now. Lithium has 3, 6, 3 is lower. You need a 2. Phosphorus 2, 2. So phosphorus is good. Oxygen, let's see, I got 6 times 3 is 18, plus 8 is 24. 8 plus 18. Wait, how did I do that wrong? Oh, that's 18 plus 8 is 26, and then another 26. So I have 26 oxygens on each side. Yeah, that's right. Usually you can show a bit more work, but I'm just to be brief. I'm not gonna. You can show the work for balancing, but so there we end up. We'd want to have coefficients and phases for everything to be balanced. If you leave the reaction unbalanced, it is wrong. So we always want to be sure that we balance our reactions at the end. But you know, one of the things about precipitation reactions, this is going to seem hard. There's a lot going on here. This is a bit overwhelming. It is putting together concepts from chapter 2 and almost everything we've talked about in chapter 3 so far. You need to be able to parse out what the ions are, rearrange them. That's double displacement. That's the reaction pattern. You need to form new ionic compounds. That's going back to chapter 2. You need to balance the reaction. So far from chapter 3, you need, or 4, sorry. And then you also need to add the phases, which are based on solubility. So this is a lot of stuff we have only recently learned. So if this feels overwhelming, because we are putting a lot together in this area. And so as a result, it's also, there's a lot of, if you can get a couple of those steps, you're in good shape. If we don't make it all the way to the finished product, you're still in good shape because there's a lot of steps to get through. And those steps involve learning the other concepts from this chapter so far. Solubility, double displacement patterns, all those sorts, balancing, all those ideas.